Have you ever looked at a towering skyscraper or a massive pipeline and thought of it as, well, permanent? It's easy to do. But welcome to this explainer, where we're going to dive into the hidden, microscopic battles raging inside the materials all around us. There's actually a relentless, invisible war being waged against these structures every single second by the very environments they exist in.
And let me tell you, this hidden war, it comes with an astronomical price tag. Get this, an estimated 5% of an industrialized nation's entire income is just swallowed up by corrosion. We're talking about replacing and protecting materials from falling apart. Think about that for a second. 5% of a massive national economy isn't going toward cool new innovations or growth. It's literally just spent to keep the things we've already built from turning into dust and rust. So, to understand this massive economic drain, here's our roadmap for today. We'll start by looking at the cost of corrosion, then zoom into the electrochemical battlefield, see exactly how iron becomes rust, explore different environments of decay, shift gears to polymer degradation, and finally, look at how we fight back.
All right, part one, the cost of corrosion.
Now, material degradation definitely isn't a one-size-fits-all kind of deal. As you can see, every category of material has its own specific Achilles heel. Metals, they primarily corrode and oxidize right in our normal, everyday ambient conditions. Ceramics are inherently a lot tougher, so they generally only break down at extremely high temperatures. And polymers? Well, they face a totally different threat, degrading from things like environmental factors and radiation. It's essentially a perfect taxonomy of decay.
To really grasp why this happens, we need to get microscopic. Let's move to part two, the electrochemical battlefield.
Zooming way in, we can actually watch where metals constantly lose and gain electrons. At a specific site on the metal, which we call the anode, a process called oxidation kicks off. This is the anodic reaction where the metal is basically the victim, forcefully surrendering its electrons to the environment. When you look at that formula, M turning into Mn plus electrons, you're looking at the literal chemical definition of a metal losing its structural integrity atom by atom.
But you know, in chemistry, electrons don't just vanish into thin air. At another site called the cathode, a complementary process called reduction takes place. The environment around the metal, whether that's a highly acidic solution filled with hydrogen ions or just plain old ambient moisture with dissolved oxygen, acts as a thief. It receives and consumes those stolen electrons.
So in this electrochemical war, there's one golden rule. The total rate of oxidation absolutely must equal the total rate of reduction. There can't be any net electrical charge accumulation. Every single electron lost by the metal victim has to be consumed by the environmental thief. It's a perfectly balanced yet structurally devastating equation.
Now that we know the rules of engagement, let's look at part 3, how iron becomes rust.
Let's apply these microscopic rules to something we literally see all the time. Rusting is essentially a two-stage chemical attack. In stage 1, the iron acts as the anode, meeting oxygen and water to form an iron 2 hydroxide precipitate. But wait, the attack doesn't stop there. In stage 2, that precipitate is further oxidized into iron 3 hydroxide. And that final product, that's what we all recognize as that familiar, flaky brown rust.
This dynamic completely dictates why some materials survive and others perish. Take aluminum, for example. It oxidizes too, but it forms a stable, dense layer of aluminum oxide, a protective shield we call passivation. Iron, on the other hand, is not so lucky. Iron forms rust, which physically flakes off the surface, and by flaking off, it leaves fresh, vulnerable iron dangerously exposed, allowing the corrosive cycle to just keep going until the metal is completely gone.
But it's not just rain and moisture causing these issues. Let's explore part 4, environments of decay.
This microscopic destruction adapts to all sorts of real-world battlegrounds. As you'll see here, you've got aqueous corrosion in water, which is heavily influenced by pH levels. Then there's underground corrosion attacking buried pipelines, fueled by moisture and soil microbes. You also have high-temperature corrosion in blazing hot furnaces involving dry oxidation, and aggressive chemical corrosion in processing plants, from things like acids and solvents. Basically, each specific environment unleashes its own highly customized form of decay.
And sometimes, we actually create the perfect environment for decay ourselves. For instance, if you simply join copper and steel tubing in a regular domestic water heater, you inadvertently create a tiny battery, because they have fundamentally different electrochemical properties, essentially a mismatch on what's called the galvanic series. This setup guarantees the steel will act as the anode and rapidly corrode right at that junction. It's a classic engineering misstep that perfectly illustrates these chemical laws.
So what happens when we look beyond metals? Let's jump into part 5, polymer degradation.
Plastics and polymers face their own inevitable breakdown, but the mechanism is totally different. Instead of exchanging electrons, polymers suffer from something called chain scission. This is where their long, super strong molecular chains are literally chopped into smaller segments by mechanical stress, intense heat, or aggressive chemicals. It's kind of like taking a pair of microscopic scissors right to the backbone of the material.
The results of this scission are just devastating to the material's properties. These aggressive chemical and environmental attacks leave the polymers fundamentally changed. The material weakens drastically. Sometimes you get cross-linking, which actually makes the plastic harder, but way less flexible. Factor in oxidative degradation just from sitting in the air, and soon you're left with polymers that are discolored, structurally compromised, and covered in deep surface cracks.
A pretty dramatic, everyday example of this is PVC pipe. If PVC is heated to 200 degrees Celsius for just a few minutes, its weak carbon-chlorine bonds begin to snap. This releases large amounts of hydrochloric acid gas. And here is the truly destructive part. That newly released acid actually accelerates the PVC's own continued decomposition. It's literally a chain reaction of decay triggered by just a bit too much heat.
So, with all this destruction going on, how do we stop it? Let's look at part 6, how we fight back. Faced with this constant, incredibly expensive threat to our infrastructure, human engineering has had to develop specialized chemical shields to stall the decay. We essentially hack the electrochemical equation. We deploy anodic inhibitors, like chromates, to forcefully create protective films right over the metal surface, kind of mimicking that aluminum passivation we talked about earlier. Or we use cathodic inhibitors, like zinc salts, to attack the other half of the reaction, starving the destructive process of the oxygen it needs to keep going.
We're doing absolutely everything we can to throw a wrench into the gears of degradation. But ultimately, understanding this fundamental chemistry leaves us with a really profound question. In this eternal electrochemical war, since nature relentlessly pushes all materials toward their lowest energy state, can our clever inhibitors ever claim a final victory? Or are we, with all our brilliant engineering, forever destined to just buy a little more time? It's definitely something to think about next time you cross a steel bridge or use a plastic tool. Thanks for joining me on this explainer, and keep your eyes open to the invisible science happening right in front of you.